Good morning to all the participants. Welcome to Module 3 of the Value Added course on renewable energy technology and its future potential. Today we'll be talking about solar energy potential and how solar energy has evolved so far in India. Solar energy demand is increasing day by day, and eventually it is disrupting the existing conventional style of electricity supply for domestic purposes. To enlighten on this topic, I would like to invite today Dr. Ahmad Faiz Minai, Associate Professor from the Department of Electrical Engineering, Integral University, who will be delivering a talk on the title Solar Energy, Plants and Performance. With these words, I would now like to invite Dr. Minai to deliver his talk.
Hello everyone, I am Dr. Ahmad Faiz Minai and topic of this presentation is solar energy, plants and performance. Overview of this presentation. This is the overview of the presentation. These are the topics I am going to cover in this presentation. First of all, introduction. Then, why do we need solar energy for power generation? In next part, I will discuss about the technologies which are used for solar power plants, that is solar thermal systems and solar PV systems. And at the end, I will explain the performance parameters of solar power plant. So let's start with the introduction. There is a pressing need to accelerate the development of advanced clean energy technologies in order to address the global challenges of energy security, climate change, and sustainable development. Solar photovoltaic is key technology option to realize the shift to a decarbonized energy supply and is projected to emerge as an attractive alternate electricity source in the future. Globally, the solar PV grid connected capacity has increased from 7.6 gigawatt in 2007 to 13.5 gigawatt in 2008 and was 21 gigawatt at the end of 2009. Similarly, annual solar photovoltaic production also jumped from 3.7 gigawatt in 2007 to 10.7 gigawatt in 2009. The growth trend is continuing and is likely to explode once the grid parity is achieved. As we know that India is located in the equatorial sun belt of the earth, thereby receiving abundant radiant energy from the sun. The India Meteorological Department maintains a nationwide network of radiation stations which measure solar radiation and also the daily duration of sunshine. In most parts of India, clear sunny weather is experienced 250 to 300 days a year. The annual global radiation varies from 1600 to 2200 kilowatt hour per square meter, which is comparable with radiation received in the tropical and subtropical regions. The equivalent energy potential is about 6000 million gigawatt hour of energy per year. The highest annual global radiation is received in Rajasthan and northern Gujarat. In Rajasthan, large areas of land are barren and sparsely populated, making these areas suitable as locations for large central power stations based on solar energy. So, the Indian government has launched Jawaharlal Nehru National Solar Mission with a target of achieving 20,000 megawatt by 2022. The goal is to make India one of the leaders in solar energy. Although solar energy is still expensive today, but costs are coming down with technology development, right governmental policies and R&D efforts. So why do we need solar energy for power generation? So the mission will be carried out in 3 phases. The Jawaharlal Nehru Solar Mission will be carried out in 3 phases and aims to do the following. First, is to create a policy framework for deployment of 20,000 megawatt by 2022. Second goal is to add 1,000 megawatt of grid solar power by 2013 and another 3,000 megawatt by 2017. The third target is for 2017 and may be higher based on the availability of international finance and technology transfer. The scheme also aims at strengthening indigenous manufacturing capability and achieving 15 million square meters solar thermal collector area by 2017 and 20 million by 2022. One of the steps to achieve this will be make solar heaters mandatory by incorporating bylaws in the National Building Code. Deployment of 20 million solar lighting systems for rural areas by 22 is also part of the scheme. This mission has received widespread support from agencies like the World Bank and the Clinton Initiative. Also the launch of organizations like the Solar Thermal Federation of India, that is we know that that is STFI, indicates that the industry is gearing up for a shift towards solar. The second one is energy security. India needs to focus on developing its own source of energy. Our major energy sources, oil and coal, are imported in large quantities. Even with the development of nuclear energy, India will be dependent on other nations for fuel. And to sustain economic growth, to come out of the energy deficit situation and ensure that energy is available in every town and village, India must utilize its immense potential in solar energy. The third is role of central and state governments. India is the only country with a ministry dedicated to new and renewable energy. There are nodal agencies in each state which specifically work on enhancing the percentage of renewable energy in the power mix, which specifically work on enhancing the percentage of renewable energy in the power mix. States such as Rajasthan, Karnataka, Maharashtra, Gujarat and West Bengal have already taken initiatives for installation large solar power plants. And of course, the reason to adopt solar energy is carbon dioxide emission, which is increasing day by day. Technologies for solar power plants. Solar power generation technologies can be broadly classified into two broad categories. First is solar thermal power plant and second one is solar photovoltaic technology. As you can see in this very basic picture, that the solar energy can be used as thermal energy and in other form in which the radiant energy of sun is converted into voltage directly using photovoltaic cell. Solar thermal systems. Solar thermal power plants produce electricity by converting the solar radiation into high temperature heat using mirrors and reflectors. The collectors are referred to as the solar field. This energy is used to heat a working fluid and produce steam. Steam is then used to rotate a turbine or power an engine to drive a generator and produce electricity. All CSP plants are based on four basic essential systems, which are collector, receiver, that is absorber, transport or storage medium, and power conversion. Parabolic trough, solar towers, parabolic dishes, and linear Fresnel reflectors are the four main technologies that are commercially available today. The first one is parabolic trough. Parabolic trough shaped mirrors collect and then reflect the solar energy onto receiver tubes positioning along the focal length of parabolic mirrors. The troughs are usually designed to track the sun along one axis, predominantly north to south. Heat transfer fluids such as synthetic thermal oil suitable for temperatures up to 400 degrees centigrade circulating through the tubes are used to generate steam through heat exchangers and steam generators and drive turbine to generate electricity through a steam cycle. This is well established and proven CSP technology. Second one is solar tower. A circular array of heliostats concentrates sunlight onto a central receiver mounted at the top of a tower. The heliostats track the sun on two axes. The central tower can achieve very high concentrations of solar irradiation, thus resulting in extremely high temperature for the operating fluid. A heat transfer medium is in this central receiver absorb the highly concentrated radiation reflected by the heliostats and converts it into thermal energy, which is used to generate superheated steam for the turbine through the Rankine cycle. Brayton cycle systems are also under testing because of the higher efficiencies. Spain has several solar tower systems operating or under construction up to 20 megawatt capacity. Third one is paraboloidal dishes. The parabolic shaped dish tracks the sun through a two-axis movement onto a thermal receiver mounted at the focal point. The concentrated beam radiation is absorbed into a receiver to heat a fluid or gas to approximately 750 degrees centigrade. This fluid or gas is then used to generate electricity in a small piston or Stirling engine or a micro turbine. Dish technology produces relatively small amount of electricity compared to other CSP technologies, typically in range of 10 to 25 kilowatt, which results in high capital cost. Fourth one is linear Fresnel reflectors. Use reflectors made of several slices of mirrors with small curvature approximating a parabola. Mirrors are mounted on trackers and configured to reflect sunlight onto elevated linear reflectors. Water flows through the receivers and is converted into steam, and the intermediate heat transfer fluid is not required in the system. These systems have lower investment cost and also lower optical performance as compared to parabolic draw collectors. This technology is still in the development stage. Solar photovoltaic systems. On the basis of its design, solar photovoltaic systems are classified into three types. First is standalone SPV system, second is grid connected SPV system, and third is hybrid SPV system. Now photovoltaic structure, we have to know about the photovoltaic structure. So first is PV cell, as shown in this slide. PV cell, it is used to convert the radiant energy of sun into voltage. That's why it is called photovoltaic cell. Whereas the output of a cell is not sufficient to produce much electrical energy. So combination of cells are used to develop a photovoltaic module. Panel is series and parallel combination of modules, while array is the arrangement of panels to produce electrical energy according to the requirement. Stand-alone solar photovoltaic systems. Solar photovoltaic based stand-alone systems used in islanding regions are generally designed as shown in this slide, which require some additional attention. The standard voltage level of such applications generally in the range of 220 to 250 volt AC. As a result, the voltage level of the DC link of the DC to AC inverter that feeds these loads needs to be maintained around 360 to 400 volt. One possibility to achieve such a high DC voltage is to use DC to DC boost converter to boost up the photovoltaic voltage. The voltage levels of the photovoltaic modules that are available commercially are generally in the range of 12 to 35 volt. Therefore, to form a DC bus of around 360 to 400 volt, several photovoltaic modules are to be connected in series to form PV string. However, with such an arrangement, the system exhibits multiple local maximum power points under non-uniform solar irradiation levels. Use of maximum power point tracking, that is also known as MPPT, using DC to DC converter varies the output DC voltage due to varying MPP voltage because of varying photovoltaic cell temperature and solar irradiance. Variable DC link voltage across the photovoltaic inverter can affect the sensitive load supply. As there is no grid in a stand-alone system, the output voltage has to be controlled in terms of amplitude and frequency. The stand-alone control is featured with output voltage and frequency controller capable of handling variable loads. Some advantages and limitations are also written in this slide. That is, it is able to provide electricity 24/7, it is totally independent of grid, and the limitations are it requires batteries for storage, and obviously when batteries are required, the system of this the cost of this system is very high due to batteries. Grid connected SPV system. The grid normally refers to the power distribution systems which receives its input power from substation at 440 volt and 220 to 250 volt single phase AC at 50 Hertz. Usually power stations have very large capacity and providing power in megawatts, but individual consumer can utilize the power in the range of 10 to 15 kilowatt. The block diagram of the common grid connected photovoltaic system is shown here in this slide. The main component in grid connected photovoltaic system is the inverter. It converts available DC power from the photovoltaic array into usable AC power consistent with voltage and power quality requirements of the grid utility. A bidirectional interface is made between the photovoltaic system, AC output terminals and the grid utility network. This enables photovoltaic system to supply power to the local loads or feed to the supply. When photovoltaic power is greater than load demand power and at night or during high load demands, the power required by load is greater than the photovoltaic generated power. The excess power required by the load is received from the grid utility. This safety feature is required in all grid connected photovoltaic systems and ensures that the photovoltaic system will not continue to operate and feed back into the utility grid when the grid is down for service or repair. So the advantages of these systems are energy demanded complemented by the grid consists mainly of only two components, solar panels and inverters, and the limitations are it is not able to work during blackouts for the reason of safety. Now the comparison of SPV systems. You can see the advantages and limitations of grid tied and standalone solar photovoltaic systems, which will modified by the next design of solar photovoltaic system known as hybrid solar photovoltaic system. It can be combination of conventional, non-conventional and any other type of energy combination with solar energy to produce electricity. Here the advantages and disadvantages of the grid tied systems and standalone systems are in this slide. Hybrid solar photovoltaic system. So hybrid system is a combination of both the previous discussed SPV systems, that is standalone solar photovoltaic system, and grid connected solar photovoltaic system, as shown in this figure, where batteries are used with grid and supports each other in need. The advantage of these systems are energy demanded complemented by the grid, excess energy can be exported to the grid, and the limitations are requires batteries for storage, and thus the cost of the system is high due to high cost of batteries. Now the performance of solar power plant. It is the very important part of any solar photovoltaic system. The performance of solar photovoltaic plant is best defined by the capacity utilization factor, which is the ratio of actual electricity output from the plant to the maximum possible output during the year. The estimated output from the solar power plant depends on the design parameters and can be calculated using standard software, but since there are several variables which contribute to the final output from a plant, the capacity utilization factor varies over a wide range. These could be on account of poor selection or poor quality of panels, derating of modules at higher temperatures, other design parameters like ohmic loss, atmospheric factors such as prolonged cloud cover and mist. So it is essential therefore to list the various factors that contribute to plant output variation. The performance of the power plant, however, depends on several parameters, including the site location, solar insolation levels, climatic conditions, especially temperature, technical losses in cabling, module mismatching, soiling losses, etc. There are some MPPT losses, transformer losses, and the inverter losses which also present in the system. There could also be losses due to grid unavailability and the module degradation through aging. Some of these are specified by the manufacturer, such as the dependence of the power output on temperature, known as temperature coefficient. The following factors are considered key performance indicator are radiation at the site, losses in photovoltaic systems, temperature and climatic conditions, design parameters of the plant, inverter efficiency, and degradation due to aging. Radiation at the site. There are some very basic terms which I will discuss here. First, beam radiation. So first of all, I have to explain what is radiation, what is solar radiation. So solar radiation is a primary driver for many physical, chemical and biological processes on the earth's surface, and complete accurate solar radiation data at a specific region are of considerable significance for such research and application field as architecture, industry, agriculture, environment, hydrology, agrology, meteorology, limnology, oceanography and ecology. Besides, solar radiation data are a fundamental input for solar energy applications, such as photovoltaic systems for electricity generation, solar collectors for heating, solar air conditioning, climate control in buildings, and passive solar devices. Several empirical formula have been developed to calculate the solar radiation using various parameters. Some works used the sunshine durations, others used the sunshine duration, relative humidity and temperature, while others use the number of rainy days, sunshine hours and a factor that depends on latitude and altitude. But the primary requirement for the design of any solar project is accurate solar radiation data. So it is essential to know the method used for method used for measuring data for accurate design. Data may be instantaneously measured or integrated over a period of time, usually 1 hour or day. Data may be beam, diffuse or total radiation. And for a horizontal or inclined surface, it is also important to know the types of measuring instruments used for these measurements. For the purpose of this report, data sources such as NREL, NASA, IMD and so on were compared. All these sources specify global irradiance measured over 1 hour periods and averaged over the entire month. The data is available for horizontal surfaces and must be suitably converted for inclined solar collectors. Monthly average daily solar radiation on a horizontal surface is represented as capital H, and hourly total radiation on a horizontal surface is represented by capital I. The solar spectrum or the range of wavelengths received from the sun are depicted short wave radiation received from the sun in the range of 0.3 to 3 micrometer, and long wave radiator greater than 3 micrometer is emitted by the atmosphere, collector or any other body at ordinary temperatures. So first of all I will explain what is beam radiation. So solar radiation received from the sun without being scattered by the atmosphere and propagating along the line joining the receiving surface and the sun. So it is also referred as direct radiation and it is measured by pyrheliometer. Now, next is diffuse radiation. The solar radiation received from the sun after its direction has been changed due to scattering by the atmosphere. It does not have a unique direction and also does not follow the fundamental principles of optics, and it is measured by shading pyranometer. Total solar radiation, the sum of beam and diffuse radiation on a surface. The most common measurement of solar radiation is total radiation on a horizontal surface, often referred to as global radiation on the surface. It is measured by pyranometer. Next is irradiance, and it is calculated in watt per meter square. The rate at which incident energy is incident on a surface of unit area. The symbol is capital G is used to denote irradiation. Next is irradiation. The incident energy per unit area on a surface found by integration of irradiation over a specified time, usually an hour or a day. Next one is solar constant. The solar constant is the amount of incoming solar radiation per unit area measured at the outer surface of Earth's atmosphere in a plane perpendicular to the rays. Next one is direct normal insolation. It is the direct component of the solar radiation incident normal to the collector, that is the angle of incidence of solar radiation, which the normal of the collector is 0 throughout the day. Now losses in solar systems. The estimated system losses are all the losses in the system which cause the power actually delivered to the electricity grid to be lower than the power produced by the photovoltaic modules. There are several causes for these losses, such as losses in cables, power inverters, dirt on the modules, ambient temperature, varying insolation levels, and so on. While designing a photovoltaic system, we have to take into consideration all the possible losses. So first, reflection losses. Photovoltaic module power ratings are determined at standard test conditions which require perpendicular incident light. Under field conditions, larger incidence angles occur, resulting in higher reflection losses than accounted for in the nominal power rating. Calculation shows that for module faced toward the equator and with a tilt angle equal to the latitude, yearly reflection losses relative to STC are about only 1%. Next one is soiling. Soiling of solar panels can occur as a result of dust and dirt accumulation. In most cases, the material is washed off the panel surface by rainfall. However, dirt like bird droppings may stay even after heavy rains. The most critical part of the module is the lower edge, especially with rather low inclinations. Soiling at the edge of the frame occurs by often repeated water collection in the shallow puddle between frame and glass, and consecutive evaporation dirt accumulates. Once it causes shading of the cells, the dirt reduces the available power from a module. The losses are generally 1%. However, the power is restored if the modules are cleaned. Next one is mismatch effect. Mismatch losses are caused by the interconnection of solar modules in series and parallel. The modules which do not have identical properties or which experience different conditions from one another. So mismatch losses are a serious problem in photovoltaic modules and arrays because the output of the entire photovoltaic array under worst case conditions is determined by the solar module with the lowest output. Therefore, the selection of modules becomes quite important in overall performance of the plant. Next one is MPPT losses, that is maximum power point tracking losses. So power output of a solar photovoltaic module changes with the change in the direction of the sun. Changes in solar insolation level and with varying temperatures. The photovoltaic panel have PV curve. PV means power voltage versus voltage curve of the module. There is a single maxima of power, that is there exists a peak power corresponding to a particular voltage and current. Since the module efficiency is low, it is desirable to operate the module at the peak power point so that the maximum power can be delivered to the load under varying temperature and insolation conditions. Hence, maximization of power improves the utilization of the solar photovoltaic module. A maximum power point tracking is used for extracting the maximum power from solar photovoltaic module and transferring that power to the load. A DC to DC converter serves the purposes of transferring maximum power from the solar photovoltaic module to the load. Maximum power point tracking is used to ensure that the panel output is always achieved at the maximum power point, and using MPPT significantly increases the output from the solar photovoltaic plant. Now the temperature and climatic conditions. Module performance is generally rated under standard test condition, that is known as STC, in which irradiance of 1000 watt per meter square, solar spectrum of AM 1.5 and module temperature at 25 degree centigrade All electrical parameters of solar module depend on temperature. The module output decreases with increase in temperature. The loss of power is defined by temperature coefficient. Now come to the design parameters of the plant. The long-term commercialization of utility-based solar photovoltaic electric generation requires the development of safe, efficient, reliable, affordable components and systems that meet utility expectations of performance and life cycle cost per kilowatt hour production goals, while allowing for full integration of time variant intermittent renewable generation resources in the utility generation portfolio. Cost reductions available through design, material specification and construction techniques developed by the power industry in response to the need for lowest cost traditional generating stations can affect significant cost savings when applied to photovoltaic generation systems. Higher generation through proper design and use of efficient system components effectively means lower cost of power. Some critical factors which must be kept in mind during design include proper selection of modules, optimum angle of tilt, minimization of ohmic losses with proper selection of conductors, selection of efficient transformers and inverters, etc. Use of reliable and long life components is equally essential for expensive solar power plant. So the actual energy output that one can expect from a given photovoltaic system depends on a large number of factors. Some of these are the photovoltaic efficiency is affected to a greater or lesser extent by the temperature of the module, usually decreasing with increasing temperature. Nearly all module types show decreasing efficiency with low light intensity. The strength of this effect varies between module types. The mounting position. For fixed non-tracking systems, the way the modules are mounted will have an influence on the temperature of the module, which in turn affects the efficiency. And lots of experiments have shown that if the movement of air behind the modules is restricted, the modules can considerably hotter, that is up to 15 degrees centigrade at 1000 watt per meter square of sunlight. Next one is inclination angle. This is the angle of the photovoltaic modules from the horizontal plane for a fixed, that is non-tracking mounting. It is also noted that the global radiation measurements are done on horizontal surface. The maximum radiation can be obtained by tilting the surface at an optimum angle, which is determined by the latitude of the location. Now the inverter efficiency, it is also a very important parameter. A solar photovoltaic inverter is a type of electrical inverter that is made to change the direct current electricity from a photovoltaic array into alternating current for use with some home appliances or to be fed into the utility grid. These inverters may be standalone inverters which are used in isolated systems or grid tied inverters which are used to connect the power plant to the grid. The efficiency of an inverter has to do with how well it converts the DC voltage into AC. The currently available grid connected inverters have efficiency of 96 to 98.5%, and hence choosing the correct inverter is crucial to the design process. There are less efficient inverters below 95% also available. Inverters are also much less efficient when used at the low end of their maximum power, and we know that most inverters are efficient in the 30% to 90%. Degradation due to aging. The degradation of solar modules with temperature and time contributes significantly to the final output from the panel. As the output reduces each year, so does the revenue from sale of power, and therefore accurate data must be available at the outset to ensure that the power plant design is exact and not over or under the required output. Lifetime of the module is one of the four factors besides systems price, system yield and capital interest rate which decides the cost of electricity produced from the module. And this lifetime is decided by the degradation rate. The effect of degradation of photovoltaic modules and arrays and their subsequent loss of performance has a serious impact on the total energy generation. And with respect to the maximum power at standard test conditions is the most critical characteristic of the photovoltaic module or array for all of its operational life. For calculation of the system size to the associated investment cost, Pmax is the key working value. The effective cost of power generation, that is rupees per kilowatt hour, is dependent on the initial investments, expected returns kilowatt hour and assumption that the module will operate for a sufficiently long period to guarantee the return of the investment. Most manufacturers indicate the extent to which the panel will degrade through the guarantee. This is specified as a ratio of the maximum power available at the time of installation. Most manufacturers claim their panel will produce 90% of the maximum power after a period of 10 years and 80% of the maximum power after 25 years. Hence, most power plants are also designed for a life of 25 years. However, since most installed solar photovoltaic power plants are less than 25 years old, this data is not available readily, and especially in the Indian scenario where solar power plants are relatively new. We have to also know about the causes of the degradation. So, various tests on module degradation are performed using real-time and accelerated exposures. These tests are conducted by institutions of international repute such as Fraunhofer Institute, the National Renewable Energy Laboratory, Solar Energy Research Institute of Singapore, and so on. These tests have successfully demonstrated that there is module degradation, and the possible reason for this are the slow breakdown of a module's encapsulant and back sheet, the gradual obscuration of the EVA layer, that is ethylene vinyl acetate, between the module's front glass and the cells themselves, and the deterioration of solar cells due to temperature increase. The silicon cells themselves have infinite life except for the slight degradation due to thermal effects. The degradation of the module itself is due to a collection of factors as mentioned previously. There are many causes for degradation, and to estimate the lifetime for degradation, standard test called type approval test has been introduced by the International Electrotechnical Commission, that is IEC. These are essentially accelerated test procedures based on accelerated climatic testing. However, there is still some uncertainty as to whether these accelerated tests can accurately simulate real-time long-term exposure. IEA guidelines recommended life expectancy used in life cycle assessment studies of photovoltaic components and systems as follows. For modules, it is 30 years for mature module technologies. For inverters, it is 15 years. For small size plants, that is for residential photovoltaic, and 30 years with 10% of part replacement every 10 years. For structure it is 30 years for rooftop and facades, and between 30 to 60 years for mount installation on metal supports, and for cabling it is 30 years. So thank you, that's all from my side. If you have any question, you can ask or send to my email address, which is given at the first slide. Thank you for listening.